Assalamu alaikum viewers. This is Hassan and you're watching my YouTube channel. Today's topic is cable size calculation for medium voltage or 11 kV systems. In the previous videos, we were discussing more towards the low voltage side and the higher amperes or higher loads. This time it would be a slight different. We are going to understand how we can select a cable for the medium voltage side. Let's start our presentation. Before going to the details, I would like to set an example in order to make sure that you will understand the selection of cable in a better way. Let's take an example of a 2500 kV transformer, and if we calculate the full load current for this kind of a transformer with the help of a formula S is equal to under 3 VI. Here we will mention uh, the 11 kV side of the system. So therefore, we select the 11 kV volts instead of 415 because we are calculating on the high voltage side. So the full load current that would be coming is around 131 amperes. Let's go to the next slide. Okay, before going into details, I would like to mention the correction factors that will be involved in the cable selection of the high voltage side. First of all, the ground temperature, which ranges from 15 degree to 45 degree, and the correction factor varies accordingly. Then after we have the ambient temperature. It is not commonly used because most of the time the cables are installed underground. Then we have the depth of the laying, that how deeply we are laying a cable from 0.5 meter to 3 meter. It's the range, and it varies from the size of the cable. If the size of the cable is less than 300 mm square, it has a different correction factor, and same if it is above the 300 mm square, so it has a different correction factor. You can see in the chart. Then the next correction factor we have thermal resistivity of soil. It is again defined in detail in this chart, and we can use the values according to our conditions. So the thermal resistivity chart shows the correction factor for single core and multi-core cables in a different way. Then we have the correction factor of grouping factor. This is again for both the multi-core cables as well as the single core cables. So these correction factors are just to remind you because that will be used later in our calculation. Let's start our example. 11 kV cable size selection according to the load. If we are selecting a transformer of 2500 kVA, then the full load current coming up to 131 amperes, and we are using one core of a cable in a single phase. The cable type we are using is a 3-core copper XLP armored PVC, and the laying method we are using is buried in ground. The ground temperature we are expecting here is 35 degrees centigrade, so the correction factor would be 0.96. If we go back to the correction factor of ground temperature, you can see here at 35 degrees centigrade, the correction factor is 0.96. Let's go back. Here you can see. So the correction factor for the depth of laying, because we are installing the cable at the depth of 1 meter, so the correction factor applicable would be 0.98 here. The thermal sensitivity of the soil is 0.8 is 2 current meter per watt, so the correction factor would be 0.81. So calculate the combined D rating factor, that would be 0.96 multiplied by 0.98 multiplied by 0.81, that would be coming up to 0.676. So let's calculate the current after D-rating factor. So the full load current is 131 ampere in this example. So if we divide it 0.76, the correction factor, the D-rating current would be 172 amperes. So we need to select a cable that can carry up to 172 amperes at least. So let's go to the cable chart and see which cable is suitable in this condition. So this is the cable table. If you go to the 50 mm square cable, here you can see it can bear up to 187 amperes. So if you go for 35, it can bear only 160. So we cannot select 160 ampere cable because our D rating current is 172 amperes. So we have selected the cable. There's a 50 mm square having the resistance value of 0.493 and the reactance value of 0.11. which can be used in our voltage drop calculation method. So let's move on. Now we can calculate the voltage drop because in the 11 kV side, it is to mention you that the voltage drop is not that much because the currents are lower and the voltages are higher. So uh, this uh, uh, this part of cable selection is not very difficult to understand because you will probably get the voltage drop up to 0.75, 0.5, 0.54. So that would be the range where you are getting the voltage drop. So anyhow, we can calculate with the help of a formula that is under 3 IL r cos theta plus x sine theta divided by 1000. So we are dividing by 1000 just because we have the length of the cable is in meters, so we have to convert it into kilometers because we have the resistance value and the reactance value is in ohm kilometer and mu kilometer. So therefore, so we're getting the voltage drop of 83.48 volts, and the voltage drop percentage is 0.75. So one over three cores, 50 square cable is suitable, which draws only 0.75 volts less than the allowable voltage drop limit as per IC standard, that is less than 2.5%. So let's calculate the short circuit current as we have mentioned in our previous videos. The same is the method, but here, if you see, we put in the values of 50 square cable. You see, the area is 50 and we are using the SLP cable, so 143.08 is the value of the constant, and we are selecting the short circuit current value at 1 second, so the duration is 1, so the short circuit current is coming up here is 7.15 kilo amperes. So there you go. On the chart, it's again you're getting the same value of 7.1, so that's how you can calculate. So what if you want to select the 11 kV cable for medium voltage switchgear? That's very important because sometimes people are considering selection of the cable according to the load conditions, but we must need to consider the condition of the medium voltage switchgear because we have already installed a VCB in there, 6630 VCB. That VCB is definitely need to be in consideration. So maximum load allowed on one feeder HSC is 5 megawatt, that is 6.25 MVA or 328 amperes. So the length of is around 800 meter. And the cable we are selecting is 3-core copper XLP armored PVC, and same other conditions, but the only difference is the total amperes have been changed. It's now 328 amperes according to the VCB. We are selecting here according to the maximum load we can put it on the VCB is 6.25 MVA in Pakistan. So in our distribution companies only allows 5 megawatt load on one feeder. So according to that, we have only 328 amperes. So if you apply the D-rating vector, the amperes are coming up to 432 amperes. So let's choose the cable from the cable table. Is that if we select the 240 square, that will be around 436 ampere. So our requirement is 432. So that would be the right size of cable. So one number of 3-core 240 square cable is suitable, which can carry up to 436 ampere per phase, greater than full load current as well as the D-rating current. So the 240 square cable is enough for this condition. So the resistance value is 0.098 and the reactance value is 0.09 for this cable. So we need to put it for the voltage drop conditions. Here is it. If we put it into the same formula, we're getting around 60.17 voltage drop, and the percentage is 0.54, which is again way less as compared to the IC standard, which is less than 2.5%. So that's not an issue again. Let's move on to the short circuit current value. Here it is. For the 240 square, if we're selecting time duration of 1 second, so we're getting 34.33 kiloamperes from this formula. And if you go into the chart, we are also getting the same value here. You can see it's between 30 and 40 and just in between the 35 and 34. So 34.33 kiloampere is the right value for the short circuit current for this size of cable. Here's a short mistake. It's 240 it's not 50 So as I've used 240 square, so the value of the short circuit is correct here. So that's it. Today's short session for you because there's not much